All right. So now that we just had our nice little half hour get to know your Greek prefixes, please refer to the ether to try to figure out what we just said when I post that PDF of stuff. But hopefully, even if you weren't here, we did do a quick little recap of Greek prefix stuff, and I'll have that as a separate set of notes in the week 1 module. So check it out if you need it. So we're going to continue on right now with some more calculations and talk about density and percents today. So if you notice, I've called this one density. Before we begin, all right. One of the things that I find peculiar about science, chemistry, is we have all these rules, we have all these things that we rely on to be absolutes in our lives. And I'm going to go ahead and tell you now, and probably tell you about, I don't know, at least 8 more times this semester. I'm going to lie to you a lot. And but the nice thing is I'll probably tell you when I'm lying to you. And I at least promise to make up for some of those lies if you come to Chem 120/121. Maine can attest, I lie a lot in this class.
Yep.
So remember when, let me put that in another color here. Remember when going from English to metric was never exact? Well, let me put this in a different color. 2.54 centimeters is equal to 1 inch.
I remember those numbers.
All right. For every rules, there are exceptions. Okay. While all the other conversions that you'll have in the test and in the rest of this class, while all the other conversions are approximations and you can get better and better at those approximations, this one is exact. I don't exactly remember when, but sometime in the early 1900s or mid 1900s, the international community got together and said, hey, we have to do something about the fact that when the US and Germany or France or anyone else gets together and works on something, we have to be talking in the same terms. And I don't mean all in metric or all in English units, because they couldn't expect us to retool all of our stuff immediately to be on metric. But they did have a problem with length scales being bad, especially for space exploration, lunar probes, and the like. Because if someone did a calculation where they said that 1 inch was 2.54 centimeters, and someone else said, oh, it's 2.5, you may think that's not a very big difference. But it is when you're launching something over 1 million miles away. Those errors compound each other, and they lost quite a number of space probes because they would just crash land into the surface because they thought they still had another couple miles to go. So the international community came together and said, we have to standardize this. We don't care if you're not coming to the SI units, but we need to make sure we don't make these kinds of mistakes. So they made the decision that 2.54 centimeters will equal 1 inch, and we're going to call that exact, period. And so a few things had to be maneuvered around, but at the end of the day, it actually saved us a lot of time and a lot of money by making this definition. Now I can hear you guys already like, wait a minute, how can they just like do this? And the answer is, what do you mean? We do this all the time. We make up parameters to fit our needs. If you think about the fact of what is an inch, it was like 3 acorns or something stacked end on end because those things were pretty uniform in size. Why did they choose those? Why not? So at a certain point, you have to make a definition in order to have a starting and jumping off point to do measurements, to understand how the world works. You have to start from somewhere. Now, this thing right here, 2.54 centimeters is 1 inch. It means it's exact. It means it has infinite sig figs. That's going to be important later. And also, I should point out, I need to know this.
One quick question.
Yeah.
So it's been like established that hey, if it's exact, it has infinite sig figs. But but I see 2.54 and I see 3 sig figs. It's like, well, why can't it be? Can you clarify the concept that something exact can have infinite?
Hold out your hand, Frank.
You can't hear me.
How many fingers are there? What do you mean I can't hear you?
Oh, okay. So, you were okay. I see. So 5.
Yeah, right. You have 5 fingers. Is that exact?
Yes.
Yeah. I mean, we basically, if you can count it, if you can define it, there are 100 pennies in a dollar. Fact. You may say, but I see only 1 sig fig in the number 100. I don't care. Anytime you make a definition, anytime you say this is how it's going to be, that is exact. You have kids, Frank?
No.
No, okay. Well, then this will be lost on you. Hey, all my parents. When you say bedtime is 7 o'clock. Yeah. Okay. So when bedtime is 7 o'clock, is that negotiable?
No.
No. Right. You have defined it. They'll go, but why? And what do you say? Because I said so. And that's what the scientific community said. Why is it 2.54? And they just go, because we said so. And you just have to accept it. So this is one of our jumping off points for a lot of the measurements that we do, especially if we're going back and forth. You do need to know this conversion. I will not give you this conversion on the exam. This is one you have to have in your back pocket. Any other conversions that go from English to metric, I will give you, but I will not give you this one. So if you need like gallons to liters or, inches to micrometers or something, I'll give you those. What I won't give is this one.
And when you say you'll give them to us,
it's on the exam.
Okay.
I have written it down and I've given you the conversion on the exam. So it'll be in a parentheses. This is the conversion, and you'll just go for it.
That'll be in a problem. Will you be able to give us an example with this in it before the exam?
Yeah. Make no mistake. Well, I've got plenty for you.
Okay.
I need to do one other jumping off point before we do one of these, and that is another, and this is actually definition.
How many exams will there be?
We got 5 in the final. Every Monday, and then the final at the last day. Another definition. So what does this mean? It's exact. Another definition is that 1 centimeter cubed is equal to 1 milliliter. And oh yeah, I need to know this. Now, this is kind of interesting. The milliliter is actually defined as the volume that water will take up if it is 1 centimeter by 1 centimeter by 1 centimeter in length, width, and height. Now, we actually know this because if you've ever watched any of those emergency room drama shows or whatever, and they bring some sort of patient in, and the doctor yells out, I need 10 cc's of epinephrine now. What do they mean when they say 10 cc's?
Cubic centimeter.
Cubic centimeters. That's
So
what they're
a
saying.
milliliter.
cc is a cubic centimeter. But do you really think someone is in the back like pouring out a liquid and trying to measure its length, width, and height to get a centimeter by centimeter by centimeter and get 10 of them? No. They're going back and they're sucking up 10 mils worth of stuff. So then I guess my next question is, why not just say, go get me 10 milliliters? The answer's simple. It is a stressed out situation. You need to communicate very quickly and very effectively. It's a whole lot easier to say 10 cc than 10 milliliters. And so they actually use the definition of this centimeter cubed being a milliliter to just get the acronym of a cc and go real fast. So there's no question and there's no delay. Now, these two things are going to be a great jumping off point for the next problem that we're going to do here. And that is we need to talk about densities and volumes. So, oh, wait, I didn't want to do that. Shoot, let me get that back in blue. Okay. So now, what I want to do is I want to talk about mass, volume, and density. Okay, mass. When we often talk about the weight of a subject, okay? Now, I'm going to go ahead and put that in quotes because they're not actually the same. Mass. This is actually defined as the amount of matter something has. This is the amount of matter something has. Now, if that cleared up everything for you, more power to you. But if you're like anyone else, including myself, that definition is kind of weird, because what does the amount of matter something has mean to you? What is matter?
Stuff.
I like it. Whoever said that, that's good stuff right there. Matter. This is just the stuff, okay? It's whatever's making you up. It's the atoms, it's the molecules, you name it. It's just the stuff that makes you up. So then my question is, how is that different from weight?
Weight has a force acting on it.
Yes, absolutely. How's it different from weight? Weight is the effect of gravity on that mass. Okay. Now, there's a reason why I put it up there that mass is, quote, weight. And then I went on to define these slightly differently, with mass being the amount of matter, the amount of stuff something has, and then weight being the effect of gravity. Why do I make that distinction? This means mass does not change. Weight can.
Wait a minute.
I'm 100.
Okay, so so what I'm getting is, if somebody wants to lose weight, so they shed their pounds, but through whatever means, their mass doesn't change.
No, actually, their mass does change. What this means, Frank, is this. I weigh 170 pounds. I go to the moon. Do I have 70 pounds? The answer is no. We've all seen the footage of those guys, jumping really far on the moon because there's not much gravity on the moon. I may only weigh a fraction of that 170 pounds, but did I lose a limb? Did I shrink in size? Did I otherwise change who I am? No. In fact, if I go to space, do I weigh anything?
No.
I don't weigh anything. So do I cease to exist? Weight is the effect of the gravity pulling on all the stuff that is you. That weight loss you're talking about, Frank, that's you burning off all those fat molecules and getting rid of them. That's different. You did change your mass, so yes, you are going to weigh less. If you're trying to bulk up and you build muscle, you're putting on more mass. In fact, that's actually a term that some bodybuilders will use, putting on mass. They're getting heavier because there's more stuff to them. Mass doesn't change, weight can, depending upon gravity. Now, let's be very thorough here, but on Earth, 1 kilogram mass will weigh 1 kilogram. They're the same. We defined 1 kilogram's worth of mass will weigh 1 kilogram. We had to. We have to have these base points from which to jump off of if we're going to do any meaningful measurements. We have to have a reference point. Now, mass is how much something weighs. Volume.
Wait, can you go back up just a little or zoom out like you did?
Yeah, no, I can do that. Slow me down.
Okay.
This lecture is going to get slow jam. I like it.
I'm good.
Oh, you're good? Okay. So we've talked about mass, and that's the stuff. Most of you have already started that lab. You get it. You go to the scale, you put something on there, it tells you a number, you're done. That's how much it weighs. That's its mass. Keep in mind, on Earth, we use mass and weight interchangeably. Just know that there is that subtle difference. Volume. So what is volume? Not Frank. Somebody else. Where's my Isaiah Danielle? Is she here? Oh, she didn't come today. But Ellen's here. I saw her.
I don't know.
Okay, that's fine.
Is it the amount of space matter takes up?
Oh yeah, perfect. Who was that?
Bella?
Oh, Bella. Oops. Have to augment my list here. Oops. Cool. Yes, actually, that is a perfect definition. This is the amount of space that the matter takes up. I know it's weird verbiage on there, and I hate ending in a dangling participle, but you get it. Right, the volume is the amount of space something takes up. Now, there are a couple different volumes that we do for measurements in chemistry. Those are the volume by calculations or the volume by differences. So those are when you have either a regular or an irregular solid to deal with. So let's talk about those two types of calculations. So first we have our volume by calculation. And this is for something called a regular solid. And all that means is we have a formula. We have an equation. We have a formula to calculate the volume. So, you know, if you have a rectangular solid, hopefully this is good old fashioned like 3rd grade. We have a length, oops. We have a length, we have a width, and we have a height. And we all know that volume is equal to length times width times height. If you had something like a sphere, then the volume would equal 4/3 pi r cubed, something of those likes. If, oh, that's a very bad sphere. Let me get a better sphere. Oh. So if we have a shape that is well defined, we have this thing called geometry, and we can use it, and we can actually do a calculation on it. And so why don't we try to do a calculation on a regular solid? And this is where we're going to get some good practice going all the way back to North Carolina. And Your Royal Highness, I think this will help in trying to cement where units go and where the values go. And we're going to do this with Forrest's first backpack. Forrest's first backpack. It's huge. I would actually almost do this life in a normal situation. I do it life size, but let's just say, here we have it. Here's all the straps. There we go. Because back in the day, those cute little backpacks for 1st graders, those things were just little boxes. I actually ran across it one time going through the back porch of my grandma's house. I decided to measure it just for kicks. So I'm like, funny, I thought it was bigger than this. It was 2.0 inches. Let me write that a little bit better. 2.0 inches deep. It was 13 inches tall. And it was 8 inches wide.
Are these real measurements?
Yeah, these are real measurements. I took out a ruler. Seriously, I thought it was bigger than this. Can anyone think why I thought it was bigger than that?
You were small.
And it
Yes.
was heavy, probably. Like stuff was in it. And
It wasn't heavy because, as my kid says, we have strong power. He uses his strong power all the time. I was like, yes, we have strong powers. But yes, I was a very small child. I was 5 foot going into high school. I pretty much didn't get much bigger. So yeah, I was amazed at the size of this backpack. So my question is, how many liters is this? How many liters would this backpack hold? How many liters would this backpack hold?
208.
Nope.
8 times 13 times 2.
No, you're going too fast. This one, by the way, I'll tell you right now, is a long problem. Because what you did, Frank, is you did a calculation. I get it. But you forgot about the most important thing in this. Okay.
You're gonna have to convert inches to liters.
That's exactly right. Frank just did the cubic inches part. He did not get all the way to liters. So here's what we're going to do. We're going to remind ourselves that we're going to liters, and we're going to start with the original volume. Now, I'm going to go ahead and do it this way I understand, Frank, that you already multiplied these out and you got 208 for the inches cubed, but I'm not going to do that. I'm going to start with the 8.0 inches times the 2.0 inches times the 13.0 inches. This right here is my volume. And I'm doing this on purpose because I have to get from cubic inches to liters. And I'm pretty sure no one in this room has that conversion rolling off the tip of their tongue, because I don't, and I've been doing this a while. But, you know, let me just say, pro tip, I wonder how we're gonna do it. Brenna, how do you think we're gonna do it?
Four centimeter equals 1 inch.
I think you said centimeters doing the inches, or
Yes.
vice versa? Okay, all right, how's that gonna help us? If we go from the inches to the centimeters, then what?
We'll go from to milliliters.
And then milliliters to?
Liters.
Yeah, that's exactly what we're gonna do. This is a long one, but just because it's long doesn't mean it's hard. We are gonna be very methodical about this, okay? Just because the prompt is long, just because the problem is long does not make it difficult. We just walk ourselves through it. So, let's take, Brenna, can you get me from those inches to centimeters?
Put inches on the
Nice.
and centimeters on the
Okay, which one's bigger, the inch or the centimeter?
inches.
So we have 1 inch is
2.34 centimeters.
2.54 centimeters.
Oh, 5.4, sorry.
Okay. What's my next step?
Meters.
Centimeters to milliliters.
Almost. Now, this is where we got to be very careful, and this is why I wrote this problem out the way I did. How many inches did you cancel out, Brenna? You only canceled out 1, didn't you?
Yeah.
How many do we have? We have 3 inches here. 1, 2, 3.
Oh,
We have to get rid of all 3, and that's okay. All that means is that we do it 2 more times. And so we have the 1 inch on the bottom again, and we still have our 2.54. That will now allow us to get rid of each of the 3 inches, which means we're left with a centimeter times a centimeter times a centimeter. What units are those?
centimeter cubed.
That is correct. So that right there now has become a centimeter cubed. And so now we're just going to easily walk our way out of the forest here. What units should go on the bottom?
Centimeters cubed.
That is correct. And on top?
Milliliters.
Perfect. And we just said that was a 1-to-1. We needed to know that. And then finally, our last set, what units go on the bottom?
Milliliters.
On top?
Liters.
North Carolina, which one's bigger, liters or milliliters?
Liters.
Okay, so for every 1 liter, how many milliliters?
There
You
is 1,000.
Yeah, that's correct. Right, because milli is 10 to the -3, so we need 10 to the +3 or 1,000. All right, so if we've done this right, and I think we just did, we have our liters like we want. At the end of the day, that will look like something like 3.4085 liters. Bless you, Your Highness.
Thank you.
So actually, because you decided to chime in, how many sig figs am I actually going to put here? Let's walk back. Woo, nice. In the 1,000 to 1 liters, how many sig figs are there?
Infinite.
Infinite. In the 1 mil to 1 centimeter cubed?
Infinite.
Infinite. All right, Miguel. In the 2.54 to 1 inch, how many?
Infinite.
And infinite and infinite. Done. How many in 13.0?
3.
2.0
2.
and 8.0?
2.
Therefore, this number should be rounded to,
2 sig figs.
which is going to be
3.4.
nice. So essentially, I couldn't put two 2-liter soda bottles in my backpack. That's how massively large it was.
I had a question. What did you divide to get 3.4?
What did I divide? The 1,000 probably did it. Is that what you're missing?
Yeah, so like the top column, you don't multiply 3.54 3 times, right?
2.54. And yes, you do it 3 times.
So could we
That's
go over?
why that's why I put all of it right there as you see it. So again, I think I see what you guys are asking. So basically this is 8.0. And let me get a big bracket here. 8.0 times 2.0 times 13.0 times
Yeah,
2.0.
that's what I was missing. I didn't have the 8, the 2, or the 13.
Okay. And I'm going to leave out all the ones if you guys are okay with that. And I'm dividing that by 1,000.
Okay, that makes sense. Thank you.
I have a question.
Yes.
Why did you use 2 sig figs instead of 3?
Because the 8.0 and the 2.0 only have 2 sig figs. And this is multiply and divide. So we always go by the least in multiply and divide.
Oh, okay. Thank
Now
you.
remember, that's different than add and subtract, so be careful. But most of the things we'll do will be multiply and divide. So
What's different about addition and subtraction?
Can you put the
that's that line trick. You remember when we drew those lines?
Yeah?
Yeah?
I think I don't exactly remember completely.
Remember when we drew these lines?
Oh, okay, yeah.
I will say this, Ming, having these notes just like bam, it's kind of cool.
Yeah.
You put the black box.
I still hate online teaching, but it is kind of cool to immediately just go back to a set of notes and just point it out. It's kind of cool.
Yeah, there is some perks.
Yeah.
Can you put the box back that you just deleted?
Can I what?
Put the box back that you just deleted that had the everything you just did.
It's there.
Oh, divided by.
Go up a little.
Hold on, I'm getting my little tool back. There you go.
Okay, perfect. I just wanted to make sure that I had it right.
Yeah, no, that's fine. I normally don't leave that in notes, but I'm okay to leave it in there. That's totally fine. All right, so if we have a shape that has an equation, we can just plug and chug and we can get a volume. So whether it's a rectangular solid, a sphere, a cone, a trapezoidal parallelogram, if it's got an equation, we can do it. Before I go on, do we have any questions about what I just did with this, quote, super long and super hard conversion? It really isn't that hard when you just lay it out, right? We have 3 inches to get rid of. We have to do it 3 times. That's the big freshman mistake, is people only do it once and forget about the other 2.
Well,
That's the reason why I wrote the all 3 out. So be careful.
When we're dealing with volume, will it always be like this? Well, I guess like for argument's sake, base times width times height. Like.
Yeah, for what you guys are going to be doing, or I would give you the equation. I know that very few of you know your geometrical equations for this, but pretty much everyone knows the length times width times height.
Okay.
But does anybody have questions about this order of operations or what we were doing here? Because that's about as hard as it gets. Your Royal Highness, you all right?
Yeah, I'm good.
Cool. You have to change your name, Sarah. You just gotta, you know, full on own it and go with your Royal Highness as your name.
Okay.
All right, so what happens if it is not one of those regular solids? Well, now we got not volume by calculation because there's nothing to calculate. What we have now is volume by displacement.
I'm
Now-
sorry.
Right?
And the first one was defined as volume by just calculating the dimensions.
Yes, but what if you can't? So volume by displacement is when you have an irregular solid. What do I mean by that? No equation. And so here I have a potato. Now clearly, potatoes are not a defined shape. Can we all agree on that?
Yes.
Yeah. So the question is, how would I determine the volume of my potato? Basically what you do is put it into a container and see how much water it displaces.
Can you go up a little bit, please, real quick?
Can do. I really apologize. For some reason, my handwriting is really bad today. I don't know why I have bad handwriting days. Hopefully tomorrow or Monday it'll be better. I'm trying to slow my hand down, but it's just not working. Okay, so when we are doing this type of experiment, what we're going to do is we're going to take a graduated cylinder, and you guys will see this when you do the lab thing. And so let's see. So let's say that this is 20 and that's 30 mils. And I'm going to put some water in here. This water is going to fill up the bottom. I'm not going to draw the rest of this graduated cylinder, but suffice to say that it's still going down all the way down to 0, and we have water in there. What I'm going to do is take this potato. I'm going to drop it in. If I drop it in, I'm pretty sure we're all comfortable with the fact that that water level is going to go up. Yes?
Yeah.
Yeah. So let's say that I do that. Sorry for the dead air here, guys.
Can you scroll up a little bit? Okay. Thank you.
So let's say that I dump in my potato. My potato is down here in the water now. it keeps morphing its shape because it can. It's a mutant potato. Well, let's say that that water level now rises up like this. Now, what I have drawn here, oh, let me get the rest of my water in here so you can see, oh, there's the water. What I've drawn here, by the way, you see that little curve thing of the water, that curvature. That's what we call a meniscus. And you'll see that when you do the lab the lab module. The meniscus is that curving of the water. Water likes to wet glass. It likes to cling to glass. And so when you pour water into a glass container, it will tend to sort of walk up the sides of the container. So when we do these measurements, we always read at the bottom of that meniscus, at the bottom of that sort of curvature, because that's where the glass is not going to be interfering with the volume measurement. Now, as we look at this measurement here, the first one over here, right on the line, is 20.0 milliliters. On the other one, you'll notice that I've got a little bit in between the 27 mark and the 28 mark. And when you do the lab, it'll talk to you a little bit more about how those measurements are done. But when I'm in between two marks, especially on a graduated cylinder, I'll basically split that difference. So this would now be 27.5 milliliters. Is everyone okay with what just happened there? I love silence. That means yes.
Yes.
Cool. So then my question is, what's the volume of my potato?
7.5 milliliters.
Absolutely. So the intuition here says, look, if it started at 20 and it goes up to 27 and a half, then that potato must have been that 7.5 mils worth of volume to push that water up. So basically you just take the volume is equal to that 27.5 minus the 20.0 to give you 7.5 milliliters. Now, where would I draw my line? Ooh, wait, who's the person who had the question about the line? It was it Bella or Brenna or shoot, who was it? Who had the thing? I was gonna show you. All right, well, they probably left the room. Just remember, now that we're not doing multiply and divide, we're doing add and subtract. We have to draw our line, and we'll draw our line at the number we know the least about. But it turns out we know both of them out one decimal place. So this just goes ahead and stays at 7.5 milliliters. We're going to report the same number because they both went out the same decimal place. Now the volume by difference or displacement is very useful when you have a shape that just won't do what you want to do. And now in your lab, it's a rubber stopper that is slightly conical in shape, so you can't use the cylinder equation on it. And you basically fill up a graduated cylinder, read it, drop in your stopper, read it again, you'll see what the volume is of that. In fact, you'll end up getting the density of it. We'll talk about density here in just a second. Now, you can do mass by direct measurements. You can also do mass by difference. So in the case of liquids, when you can't just pour a liquid onto a balance, you're going to have to figure out how much something weighs. So I want to discuss weighing liquids. It is easy to get the volume of liquids. You use a graduated cylinder, you use a pipette, a burette. All of these will measure the volumes very easily. The problem is getting the mass. The problem is getting the mass. I'm going to say problem in quotes. And the reason why I say it's a problem is it's not a problem. We can get this by doing a mass by difference. If we can do a volume by difference, and we just take the final minus the initial, we can do the same with a mass. The problem is getting mass. The solution, we'll do mass by difference. And we've shown you this in the lab, but I'm going to go ahead and go over it here because you won't have the luxury of physically doing it. So I'm going to try to give a little extra here to try to cement what's going on. So mass by difference is very akin to any of us who have small pets who do not behave, i.e. my cat. If I want to know how much my cat weighs, I can go ahead and take him to the scale. I can go ahead and put him on the scale. Think he's going to stay there? No. So how do I figure out how much my cat weighs?
Drug the cat and then put it on the scale.
You weigh yourself. And
No,
then
dear diary, Frank. Dear diary, my gosh. What was that, Carolina?
Fuck with cats. It's pretty crazy.
I don't know, you'd weigh yourself and then hold the cat and weigh yourself again. I don't know. That's how I do my suitcase.
That's exactly what you do. That's exactly what you do, Laura. You weigh yourself so that you know how much you weigh. Then you just pick up the cat and you weigh again. However much heavier you are, it was all due to the cat. So what I mean is that you can take, say, a nice little Erlenmeyer flask here, and you can weigh it. So this is a flask. And let's say that it weighs 100.329 grams. Then what I'm going to do is I'm going to put in 10 mils of water. Probably should have done this in different colors. I probably should put water in blue. But water is going to be in red right now. All right, so there's my H2O. If I weigh it again, and it now weighs 110.413 grams. So I'm going to put it in approximately 10 mil. What's the mass? I just subtract them out. You got 110.413 minus 100.329. Use my Mamma Jamma brain here. That'll be a 4. That'll be an 8. That'll be a 0. And we'll have 10.084 if my brain math works. Ta-da! There's more than one way to make sure you can get all the quantities you need. Now, I started this out by saying we were going to do mass, volume, and density. So let's talk about density and what that means. Let me see here. Hold on. There's something going on in the chat. Let's see. Are there any questions here? Is the lecture being recorded? Yeah. Oh, yeah, it's being recorded. Basma. And I do post the notes. So
that was at the beginning when we were going over the homework.
Oh yeah, I didn't record the homework part. I didn't think it was going to be that long. So sorry about that.
Yeah, but that's on the chat. That's
yeah, and the other thing, the other problem is, like, I don't know if you guys have noticed, but they're 2 hours long, and it takes me, with my wonderful internet speeds, takes me a long time to download and even longer to upload. So that's why you see them being posted at like way late in the day, because it's taking me a long time to do it. So I try to limit how much I'm recording just so that I can get the stuff back out to you pretty fast.
Can you scroll up real quick so I can mass by difference example you gave? Okay.
Are you good?
Yeah.
Okay. So now we have the masses, we have the volumes. Let's talk about density.
Hey, Forrest. Are you
Yeah.
go over the volume of a sphere or a round solid?
If you need that equation on the exam, I'll give it to you. The only one I expect you to remember is length times width times height. But
Oh,
in any
okay.
of it's just a plug and chug. So
It's one of the lab questions. Just wondering how important it is to know.
well, if you were to ask me, I think knowing the volume of all regular solids is incredibly important. So knowing that the cylinder is the area of the base times the height, or a cone is 1/3 the area of the base times the height, and things like that. I love geometry. I think it's very, very useful in everyday life. So I would say they're all important.
But for the test.
But for the test, that's a different story. I expect you to know length times width times height. And if you need the other equation, I will give it to you and you can just plug it in.
Gotcha. Thanks.
Yeah. But other than that, all right, density.
I lied. Can you scroll up just a little again? Okay.
So what is density? At this point, someone usually says how dense something is. And then someone says, oh, it's how heavy something is.
How concentrated something is.
Mass divided by volume.
And then someone's just going to go, it's the mass divided by the volume. So we have all of these monikers to dance around the idea of what density is. We'll say, well, it's how heavy something is. Well, you're thinking about whether or not it will sink or not. But remember, heavy is a mass. Someone will say, like, how concentrated it is. Yes, but we use concentrated more in terms of solutions later on in the class. Someone will say, like Frank did, is the mass over the volume. But I think that's a little disingenuous and fails to get the flavor.
Like the weight in relation to how much space it takes up?
Yeah, something like that. So the amount of matter over the space it takes up. And really what we're talking about here is mass over the volume. And it's given the equation D equals M over V, or rho equals M over V. If you're going on in your sciences, you'll want to learn rho equals M over V because that's used in the sciences. D is used for derivative. So if you're not going very much further, don't worry about that other equation. If this is the end all, just go with the D equals M over V. It's totally fine. Now, density equals the mass over the volume. Just remember, if it is more dense, it will sink. If it's less dense, it will float. If it is denser, it will sink. If it is less dense, it will float. We all have that intuitive into our brain. We have a little demo that we do that actually shows this, both a video, my colleague did a video, I took some pictures. Hopefully, it'll just be one of those other little things that cements it in. But let's talk about what it means to do one of these calculations. So let's
Can you go up a little bit, please?
Yep. In fact, let me look something up here. While you do that. So how about No, that didn't work. I'm trying to make up a problem here real quick. So we'll see how well I do with this. Because I forgot that I was going to do this today. All right, let's do an example. Let's say that I have a block of iron here, or a block of something. And let's say that it is 2.0 centimeters by 4.0 centimeters by 1.3 centimeters. Hold on a second. And it weighs 89.232 grams. What is its density? Well, if we have density equals mass over the volume, we already know what the mass is. That's 89.232 grams. And the volume we know is going to be length times width times height. So we can go ahead and put that down here as the 2.0 centimeters times the 4.0 centimeters times the 1.3 centimeters.
10.4 centimeters.
I wouldn't do that, Frank.
No.
So, and the reason why I don't want to do that, even though you are correct, is this is all one calculation. And while it's okay to do some of it piecemeal, if you're going to do that, please do not round your numbers before you get to the end. Because if you round before you get to the end, you'll incur what we call rounding errors. And your answer may start to deviate from the true answer. As much as I can, I will always keep all the numbers in the calculation so that I never accidentally round before I do the next step. So just be careful if you're going to calculate something and then use that value, make sure you're using as much of that value as possible before the end.
When you say that, do you mean plugging into the calculator 2 as opposed to 2?
So what I'm telling you, Frank, is you just told me that this was 10.4 centimeters cubed.
Correct.
What I would hate is because I know that that's actually the number, is what if you had a different situation where it was 10.4392168, but you just decided to get rid of all those when you use the number again. You will lose all of this information, which may influence your value at the end. Okay, so if you're going to do all that calculation, go ahead and do it, but make sure you use all of the digits until you get to the end. Just be very careful.
Okay.
Now, at the end of this, what is that value that you get, though? If you do this whole calculation.
8.58 grams per milliliters.
8.58 grams per, say it again, Bella. It's not mils.
Milliliters?
It's not mils. What is it?
Centimeters cubed?
There we go. Now, while they are interchangeable, we did do this in centimeters cubed, so we should keep it in centimeters cubed. Right? Because a centimeter times a centimeter times a centimeter is a centimeter cubed. But how many sig figs should we have at the end of the day?
2.
2, because of these guys right here. We only have 2 sig figs sitting right there. Actually, all 3 of them are only 2 sig figs. So this will now become 8.6. Now, Frank,
Yes.
the other reason why I caution you is if you had done this 89.232 and you divided it by your 10.4, right? And you got your 858 and you weren't careful, how many sig figs would you have used?
3.
Yeah. So that's the danger there. Someone actually asked me in the office hours, I think it was yesterday or the day before, do we always go back to the original measurements? And the answer is absolutely yes. So even if you did this, Frank, you just go back up to the original problem. You're like, oh, but all of them were 2 sig figs. Therefore, stay down here with the 2 sig figs. So even if you did that, you can always go back to the original data and look at those, the sig figs on the measurements to help guide you on the sig figs total.
Okay.
Okay.
So for density, if you ever ask us a question about density on the test, we will always use this, this formula, and it'll always be this kind of problem.
Well, see, here's the trick. First of all, it is a very rare circumstance where I will ever agree to an always and it's just. So the answer there is no. I could do a problem where your volume was given to you based off of a displacement. But it is always going to be density is mass over the volume. So whether I do it by a displacement or whether I do it by a calculation, it doesn't matter. But what I won't say is that the problem I'm going to give you is always going to be a length times width times height, and it's always going to be this, because that's not how life works. It's not. This isn't a study in always, because life doesn't work that way. So you will have the information of masses. You will have the information of volumes in one form or another. Or you could be given the density and asked for one of the other 2 quantities. Keep in mind, we have this equation right here. We could use any 2 variables to get to the 3rd variable. So I guess the answer is no, it's not just. If a block of material has a density of 3.85 grams per milliliter and weighs 0.785 grams, what is its volume? So in this case, we have a density equals mass over volume. And I've asked you to get me its volume. All we have to do there is solve that equation for volume. And we get volume equals mass over the density. And we can plug it in. So the volume is equal to 0.785 grams. And we divide that by 3.85 grams per milliliter. And boy, this is a tiny little block. Because I made up my numbers wrong. Well, actually, I can fix that. Let me fix that so the numbers are better. 7.85. Oh, I love the magic eraser. I'm just going to move some decimals so that our volume looks a little bit better. The process is still the same. You end up with 2.03896. It just keeps going out. Grams go away, we're left with our mils. What's our final number going to be?
2.04.
8.04, because we have only 3 sig figs everywhere, and that 8 is going to round it up. And we are left with the units of milliliters. Now that's not as hard as these calculations get. Do we have any questions about how that's gone about?
My question is, and because it's still a little early for me. So if we have density equals mass over volume and volume equals mass over density, then mass equals
VD.
Sorry.
We can go over algebra after class.
Oh, okay.
I'll give you guys some math stuff if you guys want some help on math after the class. All right, I've got 2 more things to talk to you guys about. Temperature and percent. All right. Temperature. Neil, you here?
Yes, hello.
All right. Neil, what is temperature?
How hot or cold something is?
Ooh, I love it when someone just gives me that. All right, here we go. This is quote, how hot or cold something is. Now, that is the definition I expect everyone to just roll off their tongue. But for once, I have to give you the high and mighty definition because we're going to use it a little bit later in this class. The official definition of what temperature is it is a measure of the average kinetic energy the measure of the average kinetic energy of the molecules of the system. That is the much more scientific way of doing it. And there's a lot of very powerful statements in that definition. I want to take a look at it and break it down a little bit. All right, kinetic energy. What does that mean?
It's like, isn't it when something moves? Kinetic is.
Kinetic energy, right? We are moving. The moving energy. What's the average mean? In the middle, right? Okay. Some are moving faster, some are moving slower. The average. Some faster, some slower. So we have the average moving energy of the molecules. What is the system? That's the weird one. This is what you are looking at. So whether you're looking at the temperature of water, the temperature of the chair you're sitting on, the temperature of your coffee, The coffee is your system. The chair is your system. The water is your system. So these molecules, even though your chair looks like it's not going anywhere, it is moving. Those molecules are moving. They may not be moving around like water does, but they're vibrating back and forth. They're jiggling. They have a movement energy within themselves, even though they don't look like they're going anywhere. Those molecules are vibrating, they're doing stuff, and they have a temperature as a result. Now, because everything can have a temperature, we need to talk about our scales. Now, first of all, I just want to ask a question. How long have we known about temperature? This is kind of a crazy thing. Let me point something out. Little history lesson / what's going on. Okay. In 1724, there was a guy that was called Mr. Daniel Gabriel. Daniel Gabriel Fahrenheit. By the way, he lives between 1686 and 1736. I want to point this out. He based his scale on the coldest ice water slurry he could make. Now, one of the ways he did that is he could pour a bunch of ice into the ice water and keep depressing the freezing point of water to get it really, really cold. And then he actually used other things beside that to really lower the melting point of water and get it colder and colder and colder. For anybody, North Carolina.
Yeah.
You hear? Hey, in wintertime, does it ever get not so pleasant over there?
Yes, it's not.
Yes. And does it ever get very icy on the roads back there?
Yes.
Yes, it does. Now, when it does get there, that little iciness, what do they do to make sure you can drive on the road?
They pour salt on the road.
That's exactly right. Because when you pour salt on the road, you will actually depress the freezing point and you will make the ice melt. And this is essentially what Daniel Gabriel Fahrenheit did. Oh, Daniels, by the way. It's Daniels Gabriel, sorry, got my S. Now, when he does this, he basically says, I'm gonna make that 0, and he starts putting tick marks up, and he starts changing the concentration of his stuff until he finally gets to where pure water freezes. Now, many of us are familiar with the fact that that makes water freezing at 32. He bases his scale on the coldest ice water slurry he can make, and he calls that 0. Makes tick marks. And he notes that pure water freezes at 32. He makes 180 ticks. And that's where he finds the water boils. He basically says, look, if boiling and freezing are opposite ends of the scale, I'm going to put 180 degrees between them and mark it out accordingly. Hence, 32 degrees Fahrenheit and the 212 degrees Fahrenheit for melting and boiling. Now, as we look at this, it's kind of interesting. I said, hey, we have to have some sort of benchmark, some sort of jumping off point if we're going to be doing measurements. Now, what Daniels Gabriel did is he took and he said, okay, I'm going to make the coldest thing I can. I'm going to call that 0. From there, I'm going to change the concentrations of things until I get to pure water. And from there, continue to heat it up, marking the ticks as we go along. And he gave us a nice little temperature scale. That's kind of cool. Here's where the history lesson is kind of even weirder. Look at the year he gives this to us, 1724. Now, I'm pretty sure that this is currently lost on you guys, so let me be very clear. Before the year 1724, we did not know how hot things were. We did not know how cold things were. I want you to think about that. So many things we take for granted in our lives of like, oh, well, we just know this. Well, no, we didn't.
So
in the year 1800, somebody says, hey, Buford, how cold did it get last night? He goes, well, 2 cows died. I mean, that's what they did. They said they had no basis to say how hot or cold things were. That is kind of bizarre. We take for granted that we can just like dial up the internet and go like, oh, it's going to be, 85 degrees today. And we know what that means. We didn't know what that meant until 1724. We haven't known about temperature very long. Which always blows my mind. Does anybody here bake?
I just made peanut butter cookies and they were so good.
My boyfriend owns a bakery, so.
Okay, so here, Sonia, I want you to riddle him this, because this just really it blows my mind. We've been baking bread for what, 7,000 years?
Yeah.
Right? How the hell did we bake bread? I mean, seriously, go tell him to bake a loaf of bread without using a temperature controlled oven.
Yeah, he would freak out.
Right? I mean, does this not like make you guys go, well, holy crap, how did we do this?
Yeah, I mean, with so much stuff, like not even just this, but yeah, like there's so many things I think like, dang, how did they do this back then? Like, how did they make it work? It's
yeah, exactly. Because they made some really good pastries. I mean, they made really good loaves of bread. They made cakes. They made all this stuff, and they had zero way of telling that they were at the right temperature. They had zero way of gauging it. Because let me tell you, you bake a lot of stuff at 400 Fahrenheit. You ain't putting your hand near there and saying, yeah, that feels about right.
Right.
It's crazy.
I know.
It's crazy. When I stop and I think about it, it's crazy. Frank, is that you?
I was covering up my mic and I thought it was working. I'm sorry. That's my boss calling. He can wait.
Oh, yeah. You can tell him take this job and shove it. I ain't working here no more.
That's kind of what I did. Not like we gotta wait until like.
We'll talk about it after class. I want to get on this roll. This is great. Check it out. Daniels Gabriel Fahrenheit gives us a temperature scale. Check this out. Once he does that, everyone goes like, oh, that's kind of a nifty idea. But the problem was he based it on the coldest thing he could make. The problem is only a few years later, they made something colder. And he's like, well, shit. Now I have to, but this is, no. And in fact, the international community said, I don't like this. Because if we can mess with the baseline of 0, then it's not a good baseline. So in walks this guy in the year 1742. All right, only less than 20 years later, 1742, there was a guy named, oh, by the way, just let's be very clear, Daniels Gabriel Fahrenheit, what scale did he give us? The Fahrenheit scale, right? Yeah. Listen, if you're smart enough to make something, you're smart enough to put your name on it, right? So in 1742, there was a guy named Anders Celsius. By the way, he lived between 1701 and 1744. What temperature scale did he give us?
Celsius.
Ah, very good, right? Gives us a Celsius scale. Now, what he does is he bases his scale, and very much akin to Fahrenheit, but a little better, bases his scale on the freezing point and boiling point of pure water. Because if people are going to start talking about the same thing, they have to be able to reproduce that temperature scale. They have to be able to reproduce essentially their thermometers. And if the coldest thing that you can make is not always the coldest thing you can make, then everyone's temperature scales will be off. So he goes, look, the rest of everyone in the world has water. And we all know water freezes. We all know water boils. Why don't we just base it off of that? And so what he said is we'll do the freezing point, and that's going to be at 0 degrees Celsius. And because right now is about the time that they're making the metric system in general, right around the turn of the 1700s, they were trying to make the metric system. He says, look, everything's in powers of 10, freezing point 0, boiling point 100, we'll call it a day. Make your check marks and go for it. Yes, I know there's zeros or negative numbers in there, but at least we can all talk the same numbers, talk the same language. You put your thermometer in ice, there you go, it's 0. You put it in boiling water, there you go, that's 100. Make your tick marks. And suddenly people can do a lot of experiments and compare notes. Now, there's a problem, however, in both Fahrenheit and Celsius, and that is the negative number aspect, because there are several calculations that we need to do wherein if we have negative numbers, things don't make sense. And so we have our third temperature scale. That third temperature scale comes to us in 1848, so about 100 years later. There was a guy named William Thompson, and he lived between 1824 and 1907. Now, Mr. William Thompson gave us the temperature scale of Kelvin. Now, you may ask yourself, wait a minute, Mr. Fahrenheit here named it after him. Mr. Celsius named it after him. Mr. Thompson, huh?
His wife. It had to be his wife.
Actually, no. For his efforts, he was actually knighted. And because he gave us the scale, he changed his name to Lord Kelvin. Back in the day, if you got a knighthood, you often took on a new name. And so he's like, hey, I made this scale. I called it Kelvin. Guess what? I am now Lord Kelvin. It's kind of cool. Now, what does he do? He bases everything on absolute zero. Bases everything on absolute zero. Now, absolute zero is where everything stops moving except for the electrons around the nucleus. There are experiments where you can actually, and very accurately, get down to what 0 Kelvin would look like. Two things I want to point out. Bases everything on absolute zero. This means there's no negative numbers. That's good for calculations. The other thing I want to also note is there are no degrees Kelvin. It is just, here we go, North Carolina. This time it's just Kelvin. By the way, this is a capital K. We can't use lowercase because that's going to be kilo. All right. Go ahead.
You said everything stops moving at absolute zero, except just like electrons and like, you know, like the little bits.
No, just because if the electrons stop moving around the nucleus, they would fall into the nucleus, collapse, and basically life as we know it would cease to exist. What I'm saying is they no longer jiggle, they no longer vibrate, they no longer do anything, they're just stuck.
And that's what happens at absolute zero.
Yeah. It's kind of cool.
So just everything stops moving. Okay.
Except the electrons around the nucleus.
The electrons.
Yeah, it's kind of a crazy concept, but I want to point something out here, by the way. Couple little fun facts. Daniels Gabriel. Okay. He gives us a temperature scale in 1724. A mere 12 years later, he kicks the bucket. Look at Anders Celsius. Gives it to us in 1742. In 1744, kicks the bucket.
And they were really young.
And what was that?
They were young to die.
Yeah, they were relatively young. So here's my advice. Don't discover anything.
For real.
Right? Except, look at this. William Thompson did break the curse. Here it is, 1848. He lives to be 1907. And I do want to point something out here. While Anders was about 40 years old when he made his great contribution, look at Mr. William Thompson. How old was he?
Like 83?
No, he was 24 when he figured out the Kelvin scale.
Oh, I figured it out.
Yeah. So if you don't feel bad about your accomplishments already, just think about this guy about 150 years ago who basically gave us the temperature scale that everyone uses and lived out the rest of his days peacefully. I pretty much feel bad about myself now.
I feel so lazy.
Well, I can't help that, Frank. All right. Now, do you need to know the history lesson? No. I like the history lesson because it puts things in perspective. Here's what you want to know. We got some equations. Degrees Fahrenheit is equal to 9/5 times the degrees Celsius plus 32. Degrees Celsius is equal to 5/9 times degrees Fahrenheit minus 32. Those are in parentheses. And finally, Kelvin is equal to degrees Celsius plus 273, or if you really want to get down to it, 273.15. I don't care which one you use.
We only need to know the Kelvin, or we need to know both? Oh.
So in actual, like it's actually 273.15, but when we do the calculations, 273 is okay.
Yes.
Okay.
So I hope I answered your question, Your Royal Highness. I will expect you to know the Kelvin to Celsius and vice versa conversion. The other two, they're a little more involved, but so one of them will be given if you need it. Now, I'm actually not going to do any of these calculations because they are just plug and chug, and I'll let your homework do those for you. The one thing I will point out, though, is you do want to be familiar with these conversions of Fahrenheit and Celsius, because many of you are going to be going into the health occupations fields, and you have to be able to talk the same talk, okay? What I mean by this is back when I was teaching at American River College as a part-timer, Sacramento has a large Russian and Ukrainian population. And true story that some of the people that were in my class were coming back to become, you know, RNs and BSNs because they were licensed vocational nurses and they wanted more education to go up the ladders. And they would routinely have people call in or come in and say, hey, I'm running a fever. And they're like, okay, well, what's your temperature? And they're all like, 40. You go, 40? You're dead. What are they saying?
40 Celsius.
40 Celsius, right? They're running a fever of 100 and stuff. But if you don't know how or what they're talking about or how to go to the other set of units that you know, you can't help them very well. So you really want to be able to manipulate those equations and very quickly do the calculations so that you can make sure that when you're talking to your patients, you're on the same page.
Do we need to remember that it's 273.15? Is that what we need to enter in our calculator, or can we just put 273?
Fixed it.
Thank you.
It's just for the people who are going on, they might want to use 273.15. I'll fix you later. For us, 273 is just fine. And again, I'm going to let your homework let you plug and chug those things. All right, last topic, percent composition. So percent, we're going to see percent come quite often in this class. And we'll probably do it 3 or 4 times before the end of the semester. Percent composition is just really the part over the whole, the piece out of the entirety. And it's usually defined as being that the percent of anything, so the percent of A is equal to the amount of A over the total amount. And of course, times 100% to make you feel good about it. Now, this amount can be anything. You can have mass percents, you can have volume percents. As long as you're talking about the same set of units, it doesn't matter. It's whatever amount of that thing is over the total amount will get you the percentage. So let's say that I have 6 crayons. I have 3 red, 2 blue, baby, I love you, and 1 green. If I were to determine the percent composition of this crayon box, I'll say 6 crayons in the box. It really is this simple. So I'm just going to do it real quick for you. The percent of the red is equal to the 3 red over the 6 total times 100%, which many of you will go like, that's 50% of them are red. We'll just march down for the other 2. The percent of blue is equal to the 2 blue over the 6 total times the 100%, and that's 33% of them blue. And finally, the percent of green is equal to the 1 green over the 6 total times 100% or 17% are green.
Is this the same as like percent error, or is it something completely different?
Something completely different. Percent error is how far off you are from the actual reported value. Come to Chem 120 and we'll talk more about that. You're probably remembering this from maybe a stats course. Percent composition is a measure of how much stuff, well, how do I put this? So when you're looking at, say, normally in a class, I would say percent composition, look around, how many people here are wearing hats? And maybe there's 2 or 3 of you in the classroom that are wearing hats. And I say, how do we get the percent of people wearing hats in this class? And you'll say, well, you just take how many are wearing hats and divide it by how many people are in this class. And there's your percent of people wearing hats. That is a percent composition. It's how many people are wearing hats out of the total of this class. That's another form of a composition.
Thank you.
Not a problem. Okay. Well, hey, that's all we need to know for the exam coming up. Do we have any burning questions?
I have a question about the test. So the examples that you've given in the lectures, are those going to be like the problems you're going to give us on the test?
Yes, but they'll also look a lot like the homework problems that you're doing. So what I've done is I've taken the test bank from the publisher and I have modified them in a way that I think sounds better. You'll notice that some of the wording in your homework problems is very formal and very stuffy. And I've taken a lot of that verbiage out and replaced it with, for instance, it'll say something like, express this scientifically notated number and report it to blah, blah. And I'm like, write the damn number. So I've taken away the flowery language as much as possible and put it into the words that I would be using, but the problems will be similar to what you've been seeing in the homework so that you have some familiarity with them.
So if we do the chapter tests, then we should be in pretty good shape.
Yeah, I would say that puts you in pretty good shape.
Okay.
Can you go up really quick? Just a little bit.
Like there?
Yeah, thank you.
Got it?
And then over the weekend, if we have a question about our lab at all, can we email you, or is it?
Oh yeah, absolutely. You can email me, and if I can get the time, I can even try to Zoom you.
Thank you.
What time is the lab going to be due?
I don't know. What did I say? I forget if I said by I forget if I said by 2 or if I just said by midnight. I probably just said by midnight.
Midnight.
On Monday?
Yeah.
Oh, so we have the whole day. It's not like we need to have it submitted before class starts or anything.
Oh man, that's the problem. I'm too nice. I should have made it due.
Mine yet. I won't receive it till probably tomorrow or Saturday.
Right. So if you're one of those people that's having the snafu about the lab stuff, sucks to be you. You lose all your points. I'm kidding. Just let me know, and we'll work something out. Because the bookstore even said that there were a couple of people with like payment issues, and they were trying to get things squared away with that. So, if you're one of those people that isn't going to get it in time or won't have enough time to finish it, just let me know. We'll work it out. But don't let this like get out that I have a heart or something, because I have a reputation here.
Could we touch real quick on?
It's really, really hard to touch over the internet, so I'll try my best.
If we could talk a little bit about percent composition as far as rounding. Like for example, two blue.
Yeah. Well, two things there, Frank. You'll see the answer. So yes, I get it that it's actually 33.33 and it's actually 16.7 or actually 66666. Your problem is not going to be choosing between 33.333 and 33. Your problem is going to be choosing between 33 and 38.
Okay.
Yeah. Again, most of these problems is an exercise in being reasonable, and again, you couldn't do like one sig fig just because you have this, and you wouldn't want to say, well, I'm actually counting them, so it's infinite, so I can just do a repeating decimal. Both of those are really disingenuous things to say. Basically, the answers will be there and they'll be reasonable, so you don't have to stress out about that.
Okay.
Maria, I hear your mic.
Sorry.
Why is everyone always apologizing to me? You didn't offend me. It's okay.
Sorry, have it.
No, don't say sorry.
Okay. We sent you an email for having trouble getting the lab manual.
Yeah.
Okay.
Just keep me in the loop if you're one of those people, and we'll work it out.
Okay, thank you.
All right. Any other questions about this, or can I stop recording and then hang out for questions?
I'm good.
Frank has spoken, thus it shall be.